Welcome to the Chapter 3 of the Oil and Gas Engineering audiobook. In this chapter, we describe the work and the deliverables of the process engineering discipline. The process engineering discipline is the core discipline. It indeed defines the functional requirements that the other disciplines will implement, such as the functional requirements for process equipment, the functional requirements for the plant piping, as well as field instrumentation and automation systems. A large number of considerations taken into account in the design found their origin in process, such as safety dispositions, materials of construction. The starting point of process design is the facility design basis. The starting point of process design is the facility design basis. The design basis, such as the one shown here for a gas compressor station, shows the composition and flow of the feedstock as well as the required flow and specifications of the products. For the case of oil and gas facilities, the feedstock, which is usually reservoir effluent, varies in flow and composition over the years due to the depletion of the reservoir. Therefore, a range and envelope of composition and flow is defined in the design basis. In addition, not only the maximum capacity is defined, but also the minimum capacity, what is called turn down. Once the design basis is nailed down, the process engineer can start its work, which is to define the process scheme that will be most suited to transform the feedstock into the required products. The processes used in oil and gas facilities are always the same. This is because the feedstock is similar from one oil and gas field to another, and the products have the same specifications, such as that of kerosene or diesel oil or sales gas. Nevertheless, the process engineer must optimize the process scheme by, for instance, using the minimum number of equipment or matching the available size in the market for gas compressors and so on. Requirements such as maximum size of equipment, such as a column, might also require to be considered for specific locations. The process engineers start their work by performing process simulations using a thermodynamic simulator. Different variations of the process scheme are studied. The feedstock, composition, and conditions are entered as input data to the thermodynamic simulator, which then performs the calculations and shows the product's flows as well as composition, therefore specifications. Once the process flow scheme has been run for the various operating cases of the design basis, covering all future years of operation, all potential operating cases, the process is nailed down. At this stage, both the process flow diagrams and the heat and mass balance can be issued. The heat and mass balance shows the conditions and composition of each stream of the process scheme. The process flow diagram shows the various equipment, the process lines, as well as the process controls. Together with the process flow diagram comes the process description. The process description is a narrative in which the process engineer describes the function performed by each equipment, as well as the way that the process will be controlled in order to achieve the required products, specifications, and flow rates. We have now reached the first stage of the process engineering design. Indeed, we have defined the process flow diagrams, therefore the process scheme, and we have also defined all the operating cases. The subsequent steps of process engineering will be based on these two documents, process flow diagrams as well as heat and mass balance. First of all, the sizing of the equipment. Let's have a look at the type of equipment that we have on the process flow diagram. There are separation equipment, such as this equipment here and this column. We have heat exchange equipment, such as this air cooler or this furnace. And we have rotating equipment, such as this compressor and this pump. Not shown on this process flow diagram are additional equipment such as reactors as well as storage tanks. A different approach is applied by process to specify each of these equipment. Equipment performing a process function such as separators or reactors are completely designed, sized by process. Equipment performing a hydraulic function such as compressors, pumps, or a heat exchange function such as heaters or heat exchangers are simply specified by process, but they are not designed, they are not sized. Their sizing, the sizing of rotating equipment and heat exchange equipment, is done by the equipment vendors. So, let's first have a look at the equipment, the separation equipment, which is sized by process. This gas-liquid separator, for instance, is sized by process in order to achieve the required gas-liquid separation efficiency. Practically, this cross-section area for the gas flow is increased up to the point where the smallest droplets of liquid that are needed to be recovered in the liquid phase have their velocity reduced enough so that they will indeed fall in the liquid phase. This sizing is done for all the possible flow rates of gas and liquid of the various operating cases of the heat and mass balance. Once the sizing is done, a process datasheet is issued by process, which shows the vessel dimensions. In addition, it shows the vessel operating as well as design conditions. Design conditions are conditions slightly above maximum operating conditions in order to allow some margin in operation. For rotating equipment, i.e. equipment performing a hydraulic function, such as compressors and pumps, as well as heat exchange equipment, process simply defines the inlet and outlet conditions. Process does not perform the sizing. Process does not design, but merely specifies the equipment. The design is left to the equipment vendor. Therefore, the process datasheet issued by process is rather simple. It simply states the inlet and outlet conditions. For this compressor, for instance, process will indicate which are the inlet and outlet flow as well as pressure for the various operating cases, including the most demanding of the heat and mass balance. The datasheet of equipment which are not designed, which are not sized by process, but merely specified, such as rotating equipment, heat exchangers, fired equipment, primarily indicates the inlet and outlet stream conditions. They also provide all information necessary for the vendor to perform its design. For a heat exchanger, for instance, it will include the fouling factor of the fluid as well as the allowable pressure drop. For a pump, it will include the available NPSH. For a heater, it will include the enthalpy curve of the fluid. An important aspect is also that since process is not sizing the equipment, the required over-design to be included by the vendor is indicated on the process datasheet. This over-design is usually 10%. We have now completed the second step of the process design, which is the equipment sizing or specification. The process engineer then needs to go into more details of the plant operating environment. This is done by preparation of piping and instrumentation diagrams. The process flow diagrams that we have seen earlier only show the main process lines, the process equipment, as well as the control valves. Much more details are needed to be defined by process. These details are shown on the piping and instrumentation diagrams. PNIDs do not only show the main process lines as process flow diagrams, but all lines, including utility lines, lines used for maintenance, for equipment drainage and depressurization, lines used for startup, and all other possible use. In addition, the PNIDs show the line diameters as well as material of construction and rating. All valves are shown, not only control valves as on the process flow diagrams, but manual valves as well. All instruments are shown, not only process control instruments, but also instruments used for monitoring, as well as alarm and process shutdown. process discipline is indeed responsible to design the process and emergency shutdown systems. These systems include sensors as well as final elements which include shutdown valves. This system is designed to bring the process in a safe condition upon deviation of process parameters outside their normal operating range. The logic of operation of the process and emergency shutdown system is shown on the cause and effect diagrams. As explained, PNIDs show all the features that are provided for operation, monitoring, process and emergency shutdown, as well as for maintenance. It is therefore an essential document fully depicting the future operating facility. It is subject to a comprehensive review between the engineer and the plant owner. PNIDs must indeed comply with the operator's operation, process automation, safety requirements, as well as maintenance practices. The PNIDs are therefore subject to revision. Their initial issue is called issue for review and is reviewed during a meeting between the engineer and the plant owner, the future operator. Once the review has been held and the changes have been incorporated in the PNIDs, they are reissued in the revision called IFD, issued for design. But this is not the final issue of the PNIDs. Indeed, PNIDs must be subject to an audit called HAZOP. The HAZOP, Hazard and Operability Study, is an audit of the process shutdown system designed by process. It ensures that safeguards have been provided against all possible deviations of process parameters. If such safeguards are found to be missing, then an action is recorded in the HAZOP report for the engineer to add such a safeguard. These safeguards will be added on the next revision of the PNIDs, called the Issued for Construction revision. This issue for construction revision will also incorporate interface information from equipment vendors, such as utility lines, size of piping connections, including drain lines, vent lines, and so on. It is essential to understand the stepwise development of PNIDs. Indeed, PNIDs are the vehicle by which process defines to piping and instrumentation and control disciplines their scope of work. These disciplines needs to have a frozen basis. And this frozen basis is the IFD revision. These disciplines will start their work of piping design and instrumentation and control system design from the IFD revision of the PNIDs. Nevertheless, this discipline will not be able to complete their work, and in particular to issue drawings good for construction, such as piping drawings, until the PNIDs have been issued in IFC revision. The process operating and control philosophy describes the functional requirements of the process control system. It describes the process automations, such as automatic start of a pump and so on. It is used to program the process control system.
Process must provide information on the control valves in order that they are properly sized by the vendor to cover the entire operating range. This is done by issuing the instrument process datasheet. The process datasheet of a control valve indicates the extreme operating conditions for the valve, so that the valve vendor can select the proper size so that the valve will effectively control over the full operating range. Usually that means that the valve is not less than 20% open and not more than 80% open. 20% to 80% is the effective valve control range. We have now seen that process has specified equipment and instruments. Process also specifies pipes. Process issues the process fluids list. It is a list of the various services with their service conditions, in particular pressure and temperature. It also specifies the basic material that will resist the corrosion of this particular fluid. This list is used by piping to identify the different type of piping materials, which are called the different classes, that will be required for the plant. We have now seen how process has specified equipment, the process control system, the emergency shutdown system, the instruments, and the pipes. I believe now you understand why in the introduction I said that process writes the music for the other disciplines to play. Indeed, you see that process specifies equipment, instrument, pipes, control systems. It indeed provides the functional requirements, and the other disciplines will implement these functional requirements. A large plant contains several process units. The block flow diagram shows the interconnections between these process units. Process engineering work is usually split by unit. Therefore, the documents we have seen are issued by unit. Once the design of all these process units have been done, process is able to gather the consumption of all of them in the various utility fluids, such as cooling water, steam, fuel gas, and so on.
Process consolidates the consumption of the various units in the different plant utilities in the utility summary. The utility summary shows the consumption of the various equipment in the different utilities, including cooling water, fuel gas, nitrogen, steam, and so on. The total consumption of each utility serves as the basis for the design of the corresponding utility generation unit. You remember that utility units are designed after process units. Indeed, process units have a certain requirements in terms of utilities, and only once these consumption of utilities are known can the utility unit's design basis be established. Another summary that is produced by a process is the relief load summary. It is an inventory of all possible scenarios of relief of gas to the flare. Possible scenarios include emergency shutdown and depressurization of the plant, as well as general electrical power failure, cooling water failure, fire, and other scenarios. The maximum flare load for any scenario gives the sizing of the flare system and allows to size the flare header, flare knockout drum, flare stack, and flare tip. Indeed, the height of the flare is determined so that the level of radiation where personnel could be present is within a safe limit.
The final activity of the process engineer is to issue the plant operating manual.
The operating manual contains, first of all, a description of the facility. It contains a special focus on the process control system, which is the interface between the operator and the plant. It naturally contains detailed instruction for startup, normal operation, as well as shutdown of the plant. It also contains reference information, such as the capacity of the various vessels and equipment, the set points of controllers, alarms. This presentation of the work and deliverables of the process engineering discipline is now completed. You are now familiar with the activities as well as documents issued by process. Thank you for your attention. Goodbye.